Hello everyone, this is Mr. Kaviani, and by the end of this video you should be able to discuss the general characteristics of friction, describe the various types of friction, and calculate the magnitudes of static and kinetic frictional forces. To begin, let's define friction. When I say the word friction, you probably have some experience that comes to mind, whether it's rubbing your hands together on a hot day or sliding a box across the floor. Friction is an interaction between two objects that are in contact with each other, and friction is a force that resists the motion or attempted motion between these two objects. So let's go ahead and write that out. Now it's also helpful to define two different kinds of friction. We can have static friction or we can have kinetic friction. Now static means not changing, or in other words, not moving. So static friction is a kind of friction that exists between objects that are not moving. So in this case, friction is resisting the attempted motion of that object. So if you've ever tried to push a heavy piece of furniture or a really heavy box and it just wouldn't budge, what you're feeling is that static frictional force being too powerful for you to overcome. That's essentially a type of friction that we don't always think about as friction, but it is called static or motionless friction. On the other hand, we can also have kinetic friction. Kinetic is a word that means moving. So this is the type of friction that we're most commonly familiar with, which is friction between two objects that are moving relative to each other, like sliding a book across a table. So what causes friction? Well, if we were to zoom in on the microscopic level at the interaction between two surfaces, like I have on the right-hand side here, you would see that on any surface, even a seemingly very smooth surface, there are all of these imperfections, we call them. So I'm circling that on the right-hand side here. These little ridges and dips and hills and valleys create irregularity in the surface. And when two surfaces are in contact with another, these irregularities sort of lock together, kind of like puzzle pieces, and make it difficult for that object to move, right? We have to essentially break these ridges apart in order to get this object to start moving. This little animation in the bottom right-hand corner does a great job of demonstrating the difference between static and kinetic friction. You can kind of see here when the box is not moving, those ridges are locked together, and then once we start moving it, they're able to slide a little bit more easily past each other, but you can see that blown up right there on the bottom right-hand corner. All right, let's take another look at some key characteristics of friction. So it turns out that because friction is an interaction between two irregular surfaces, the normal force, or the force of a surface on an object and vice versa, is directly proportional to the frictional force. On the right-hand side, I have two pictures. The first shows a small normal force, or a small normal interaction between two surfaces. So you see they're not really pressed up that tightly against each other, and those ridges aren't interlocked so tightly. But if we increase the normal force, which we can do through a variety of ways, right? If we increase the strength with which those surfaces interact, then we see there that the ridges are more tightly locked together, and we get a stronger frictional force. Now, we can express the force of friction for both static and kinetic friction in terms of the normal force using something called the coefficient of friction. So let's take a look at these equations that I have listed on the left-hand side here. We know that when we push on something that doesn't really move, we're experiencing static friction. Now, friction only exists when I have something that's trying to move or is in fact moving. So what we can say is that the force of static friction is less than or equal to something called the coefficient of static friction, which we'll look at in a moment, then multiplied by the normal force, or the force of the surface on that object. And again, the reason that this is less than or equal to is because the harder we push on something, the more friction will respond up until it begins to move, right? So if I'm not pushing on an object, there's no frictional force between that object and the floor. But as I begin to push on that object, the static frictional force will increase and increase and increase up to a certain point, and that's what we call the static frictional maximum. So the second equation is sort of the greater than or equal to, it's the or equal to condition. So the maximum force of static friction is essentially the coefficient of friction times the normal force. So this is like if you're trying to move a table and you push and you push and you push, and then finally it gives. The most friction it was able to provide without moving, we call the maximum static friction. So essentially the minimum force that you have to apply to an object is got to be at least the static friction. And then anything greater than that, and it'll begin to move. And then we get something called kinetic friction, which in this case will just be equal to the coefficient of kinetic friction, again, times the normal force. So all of these are proportional to the normal force. Now, this whole less than or equal to thing can be kind of non-intuitive. So let's take a look at a graph that'll help us interpret what happens to an object as we begin to apply force to it. So this is a graph that on the x-axis shows the applied force on an object in newtons, and on the y-axis shows the frictional force, also measured in newtons. Now what you see here is that as we begin applying force on an object, kind of like the object in the upper right-hand corner of the screen here, if we push on that object to the right, we're going to start to experience a static frictional force to the left, right? We've all experienced this. The box will not budge and it'll push back against us because friction will keep it in place. Now, as I increase the force, so as I go down the x-axis here, the applied force increases, then the frictional force will also increase up until a certain point. And it's labeled here threshold of motion. This is also the maximum static friction. And right at that moment, as soon as we add any additional force, if we add 1 more Newton of force, the object begins to move. And then immediately we see a drop in the actual amount of friction. So what's happening is that as you're applying force to this object, you're continuing to push harder and harder and harder. Friction is going to resist you up to a certain amount, and that is the maximum static friction. Once it reaches that limit, it will begin to move. And then now that the object's moving, it's actually a bit easier to keep in motion. So there's actually less friction. And we'll look at this in a moment. This is the coefficient of friction here. For kinetic friction, it's 0.4. For static friction, just for this object, it varies by scenario, is 0.5. So what we see here is that as soon as the object begins moving, it's actually easier to keep moving. In other words, there's less friction when it's moving than when it's not moving. And we can explain that with that ridge and hill model that we saw earlier. When the object's moving, the ridges aren't so locked together and they're able to slide past each other more easily. So what we also see is that no matter how hard we push on it, right, this force of kinetic friction doesn't change. It's a constant value. So whatever it is, it will be that value regardless of how hard you push on it. Now, the normal force could change this, but the applied force can't. So static friction, this is the less than or equal to part right here, this slope that we see. Up until this part, we get the maximum, and then once we keep pushing on it, the friction drops and our coefficient changes. So let's take a deeper look at this coefficient of friction and see what that's all about as well. So what is the coefficient of friction really saying? The coefficient of friction is just a measurement of how strong the frictional interaction between two surfaces is. And so it depends entirely on the type and makeup of those two surfaces. I have a table on the right-hand side here from our OpenStax textbook, and you can see how the coefficients of static and kinetic friction change depending on the materials we're using. So you can imagine that something like rubber on dry concrete would be very difficult to move, right? You could imagine how much they would maybe interact with each other, right? The surfaces, as opposed to something like ice on ice, which we imagine would be very slippery and frictionless. I also want to point out that in most cases, in almost every case here, the coefficient of static friction is higher than the coefficient of kinetic friction. Again, demonstrating that when two objects are sliding past each other, there's less interaction between them than when they're locked in place and still. The reason we call this a coefficient of friction is because it's actually a unitless quantity, so it doesn't have units. And why doesn't it have units? Well, if we take the equation from the previous slide and rearrange for the coefficient, this normal force is measured in newtons, but so is the frictional force. So a newton divided by a newton, the units cancel, and essentially what this is, it's a ratio. It tells me for every 1 unit of normal force, how much more frictional force am I going to get? So the coefficient's really just a ratio telling me how much friction I'm going to get depending on what my normal force is. And again, it varies by the materials and the interaction between the two surfaces. So you don't need to memorize these. You'll be provided with these on exams and on questions, but it's good to know. And I include this table as a reference in case you're curious when solving problems. Now, there's one more very, very important thing that we have to talk about when it comes to friction, and that is the direction that it acts. This is not entirely intuitive, and this is one of the most common places I see students make mistakes, so I thought it was worth talking about. Friction always opposes motion, not any of the forces that are being applied to it. I'm going to say that again. Friction opposes motion, not the applied force. And if you think about what friction is, right, an interaction between two surfaces that are sliding relative to each other, it only cares about the direction the object is sliding. So if we know this, we can take a look at these diagrams and we can actually say what direction the box is traveling in. First of all, picture 1 on the left here, is this box moving at all, right? Well, I see that there is a net force on the box, right? The applied force to the right is stronger than the friction force to the left. So I know that this box is either going to begin moving or is already in motion because it will be accelerating. So I can answer that second question here. What direction is the box accelerating in? Well, it's accelerating to the right. How do I know this? Because there's a net force to the right. But that's the acceleration, right? That is not the velocity or the direction of motion for the box. Now, in this case, because the friction force is pointing to the left, that's the only thing I look at. Because the friction force is pointing to the left, and I know the box is or will be moving, then I know it will be moving to the right, right? The box must be moving opposite friction, or friction really is opposite motion. So I know the box is moving to the right because friction is pointing to the left. So in this case, the applied force and the frictional force happen to be in opposite directions because we're pushing it in the direction that it's traveling in. But again, this is not always the case. For example, let's take a look at the second picture. I have a box that's being pushed to the left, but I also have a frictional force to the left. So even though we can't see it, right? Let's take a look at the second question first. What direction is the box accelerating in? Well, we know it's accelerating to the left because there's a net force in the left direction. The only two forces we have are pointing left. Now, which direction is the box moving in? Well, I know it's moving because there is a net force, and so I know it will be accelerating. But the frictional force is pointing to the left. So I know that the box must be moving to the right. So this is an example of a box that is moving to the right, but is trying to be stopped or pushed against by somebody. So I know that the box is moving to the right, again, because friction is pointing to the left. So this is actually the same reasoning we used for the first picture. So again, even though the applied force is to the left, the frictional force doesn't care. It only considers the direction of motion, not the direction of the applied force. Now, in case you're not convinced, I've gone ahead and pulled up a simulation to demonstrate this fact, that the frictional force opposes motion, not the applied force. If I begin applying a force to this box in the rightward direction and I overcome static friction, the box will begin to accelerate and we see a force of friction pointing to the left because the box is moving to the right. But if I switch directions and quickly push to the left, you'll see here that while the box is moving to the right, the frictional force is still pointing to the left, even though I am now pushing on it to the left, right? So the frictional force, again, opposing motion. Watch what happens when the box stops and turns around. There we go. And now that it stopped and started going to the left, the frictional force switched directions and is pointing to the right, again, to oppose motion, not the applied force. So please keep this in mind. This is the number one thing I see students missing, is that friction opposes motion, not the applied force. All right, this concludes the concept video for friction. Please take a look at my next video for problem solving and examples involving friction.